Dear students, so far we have discussed inference procedures based on independent samples. It was assumed that the variable under consideration has been taken from two independent samples, whether it is a t-test or a Mann-Whitney test. Now we consider methods based on what is known as paired samples. Methods based on paired samples. And this method is appropriate if there is a natural pairing of the members of the population. Natural pairing of the members of the population. As an example, suppose that we want to decide whether a newly developed gasoline additive increases gas mileage, and 10 cars are randomly selected, and mileage without additive, mileage with additive, and the difference, paired difference. So, an example, n is equal to 10 number is taken, 25.7, 24.9, the difference is 0.8. In this way, we take all the pairs and the sum is 6.6. The pair differences are noted for all these 10 observations, that is mileage with and without additive. The differences are noted. Paired differences are noted. And remember this, I am not writing the examples in full because the same examples will be demonstrated using Megastat in a separate playlist. You can see. You can go through the procedure explained in Megastat using the same data. Okay. To formulate this problem statistically, we have one variable, that is the mileage, two populations, the cars. So population 1, we say all cars when additive is used, and population 2 when additive is not used, with additive, without additive. Now, mu1 is the mean of population 1, mu2 is the mean of population 2, that is with additive mu1, without additive mu2. So our H0 is mu1 is equal to mu2. Mu1 is equal to mu2. H1, mu1 is greater than mu2 or not equal to mu2, so not equal to or greater than if you are sure that the additive will increase the mileage. And we can use, in this case, independent samples to test this hypothesis. Means 10 cars are selected at random using fuel without the additive, 10 cars, another 10 cars selected at random using the additive. That is possible, but in this case, it is better to use paired samples. The reason is, if you use paired samples, any extraneous source of variation in mileage can be avoided. If you take 10 cars for with and 10 cars for without, the characteristics, the extraneous characteristics of the cars may affect mileage, and differences in mileage may be due to the specific characteristics of the cars. But if you are using the paired difference, this problem can be eliminated. So it is better to use paired samples if there is a natural pairing. Another example is the age of husband and wives. You can test whether there is a difference in the average age of husbands and wives. Similar examples can be considered. Now suppose that D is the difference in mileage between the two types of fuels, without and with the additive, and we call each difference the paired difference. Each difference the paired difference. We call each difference the paired difference because D is the difference between two pairs. D is the difference between two pairs. Now, let me give a definition. If H0 is true, then the paired differences of gas mileage for cars samples should average about 0. That is, sample mean D bar of paired differences should be roughly 0. If H0 is true, then the mean value of the paired differences will be roughly equal to 0. This is because the additive has no influence. But if D bar is positive, we have evidence that the additive increases the average mileage. And in our case, D bar is 6.6 by 10, 0.66 miles per liter, MPa, 0.66 miles per liter. Now the question is, as we have discussed in many times, is this difference due to sampling error? Is this difference simply due to sampling error, or is this difference large enough to indicate that there is a difference in the mileage when the new additive is used? And in order to answer this question, we must know the distribution of the variable D bar. We have to know the distribution of the variable D bar. That is the sampling distribution of D bar. Always remember this. Without sampling distribution, you cannot test a hypothesis. In the case of independent samples t-test, we have the distribution of X bar, pooled or non-pooled, T distribution with the n-1 degrees of freedom. Here, the random variable is D bar. We assume that we take this paired samples an infinite number of times. So you will generate D bar an infinite number of times. So you have a distribution for D bar. So this distribution must be known to carry out the hypothesis test. Formally, suppose that x is a variable in each of these two populations whose members can be paired. And for each pair, let us denote the difference between the pairs as d. D, the difference between pairs. Paired, and we call this d paired difference variable. Then it can be shown that mean of the paired differences is equal to the difference between mean of the two populations. So mean of paired difference is equal to mu1 minus mu2. Mean of the paired difference. Paired difference is equal to, that means you take the paired difference d, and calculate the mean of the paired difference. Then it is equal to the mean of the difference between populations. Also, if d is normally distributed, we can apply this equation and our knowledge about the studentized version of the sample mean in the form of a definition. Suppose that x is a variable on each of two populations where members can be paired. Further, suppose that the paired difference variable d is normally distributed. D is normally distributed. Then for paired differences of n, the variable t is equal to d bar minus mu1 minus mu2 divided by SD, that is standard deviation of the pair difference, SD by root 10. The variable d bar minus mu1 minus mu2 by SD by root 10 follows t distribution with the n minus 1 degrees of freedom. N minus 1 degrees of freedom. So the test based on this is known as the t-test. And under the null hypothesis that mu1 is equal to mu2, this becomes d bar by st by root 10. Follows t distribution with the n minus 1 degrees of freedom, and the test is known as paired t-test. So just as we say x bar is normally distributed with the expected x bar equal to mu, here we say that d is normally distributed with the expected d bar is normally distributed with the expected d bar is equal to mu1 minus mu2. Mu of d is mu1 minus mu2, and the test statistics is given. T is equal to d by st by root 10. So this can be used as the test statistics. Now let me formalize this. For the paired t, the steps are: we assume that simple random paired samples, normal difference or large samples, then H0, mu1 is equal to mu2, H1, mu1 not equal to mu2, mu1 less than mu2, mu1 greater than mu2. Then calculate the paired difference d. Then compute the value of the test statistics d bar by SD by root 10. Then the critical values are depending on the alternative hypothesis minus t alpha by 2 t alpha by 2 minus t alpha if alpha is 5% and if the test statistics in the critical region reject H0, otherwise do not reject H0. Then this is the procedure. And let me tell you some points. Do not apply this test for independent samples. And do not apply this test for pooled or non-pooled t-tests. Normality refer to D only, not for the populations. Paired difference is normally distributed, whether the populations are normal or not. We can apply for large samples regardless of the distribution of the shape. And as we have discussed earlier, if there are outliers, it should be considered. In our example, H0 mu1 is equal to mu2, H1 mu1 not is mu1 is greater than mu2. This is our H1. Suppose alpha is 0.05, t is equal to d bar by st by root 10 is equal to 4.71, and critical t value is 1.883 and p is 0.00053, something like that. So it follows that the t obtained from the sample is in the critical region or p value is too small, so H0 is rejected. Then additive increases the mileage of the car. That is our conclusion. The additive increases the mileage of the car. So we have considered 3 test statistics to compare means based on normality assumption: pooled t, non-pooled t and paired t. One non-parametric procedure was considered, Mann-Whitney, and in the next class we will consider one more non-parametric procedure equivalent to paired t, that we will see in the next class.